Hello, everyone, and welcome to Inside Unreal, a show where we learn, explore, and celebrate everything Unreal. I am your host, Dan Hutnick, and I am here with some of the folks from StateTree to talk about an overview of StateTree and how it can be used not only for AI, but for animation, UI, mission, dialogue, even cameras, and maybe more. We're about to find out. So we have a lot that we can cover here and are going to cover. So I'm going to jump in and introduce our lovely guests here. And let's start with James. Why don't you go ahead and introduce yourself?
Hi, I'm James. I'm a software engineer with our technical developer relations, so I kind of sit between licensees and end users in our development team. I happen to be embedded with the game AI team here at Epic. I write a lot of docs and guides for how things work, as well as answering questions for a bunch of studios.
Perfect. Perfect. And Patrick?
Hi everyone, my name is Patrick. I'm based in Montreal, working for Epic for the last 8, 9, 10 years. I'm a programmer right now working on the AI game AI team.
Perfect. Perfect. And anybody who's been around here for a little while knows Seb, but let's get him introduced. Seb, how you doing?
Hey guys, I'm Sebastian Hernandez. I'm a content developer right now with the Engine Labs team. I'm working on different kinds of content projects for Unreal Engine from the template overhaul that came out a few versions ago to projects like Titan sample and other samples that we have released. And it's nice to be back.
Perfect. Lovely. Pleasure to have you back. And last but not least, we have Jacob.
Hi, I'm Jacob Wang. I'm an AI programmer working on the Unreal Engine, and I've been mainly focusing on working on StateTree with Patrick. That's pretty much for me.
Perfect.
Thank you.
Perfect. Well, as I alluded to in the beginning, we have a lot that we can talk about here, and we'll be talking about. So, let's do a brief overview. What are we talking about here? We're talking about StateTree. What is StateTree? How can it be used? Let's jump right in.
Yeah, so StateTree is a hierarchical state machine that we introduced to the engine in Unreal Engine 5. It's seen lots of updates since then. We want to kind of show some of the internals for how it works, so you can understand key terminology, what the different things you're seeing inside of the StateTree editor actually do, as well as cover some of the things that are a little bit more black box. You don't get to see as much, like how do we tick things, how do bindings truly work behind the scenes, what's safe and unsafe, as well as giving you some examples of cool things that Seb's been working on in Titan to kind of make this a clear example. And then we want to take in some questions that everybody's been bringing up. We get some that we get fairly common, but we'd also love to answer anything as we're going through it for people. With that.
And with that, that's a great segue. If you have any questions throughout the show, please put in brackets question and then your question. And we have some moderators that will be collecting those and putting them into a list so that we can go ahead and ask these lovely folks all your awesome questions. So with that, I think, Seb, you might have some stuff to show off here. You ready to jump in?
Yep, everything is ready, so feel free to share my screen.
Let's do it.
All right. So I promise that this is completely related to StateTree, but right now I'm going to do a shameless plug on Titan for a few minutes. And if you're not familiar, this was a game jam that we did with the community a couple of years ago, and we have a lot of really cool environment and character content. But one of the things that we wanted to provide there was more of a tool set so you can build an open world exploration game. And that's basically what we've been working on over the past few months, right? We wanted to give you more robust NPC behaviors, dialogue systems, inventory, quest frameworks, that kind of stuff, right? And you can see some of this. This is my little test village, and you can see some of the stuff that you have here. So you can see here that we have a bunch of NPCs just moving around. Some of them are just randomly roaming around. Some of them are going to be following paths and performing different dance moves over here. And you can see that I can approach some of these guys and I can start a conversation. And so the conversations are going to be linear. We also have some other NPCs that are going to be similar to our quest givers, right? So this guy is not feeling so good, and he's asking me for a potion. But because I don't really have a potion in my inventory right now, there's not much that I can do. Fortunately, there's one right here, so I'm just going to grab it. Go over here, and now he reacts to this, and he offers to buy it for 300 gold. So let's go ahead. You can see that we have some notifications there, and this guy can go back to ruining his throat again. So because we have an inventory and because we have a dialog system, you can actually do stuff like implement a store interface, a pseudo store interface. This is basically just a branching dialog where I have different options. So I'm going to buy an elixir over here for 2,000 gold. I'm going to try and buy one again, but I don't really have enough gold. And dialog is going to react to that. So it's not going to give me. So let's go for another healing potion over here. And finally, we have the innkeeper. So right now I'm at full health. So he's not really going to allow me to rest. So let's go to my cheat boxes over here, lower my health a little bit. I can probably just use a healing potion too. Oops, I healed back to full health, so I'm going to have to lower it again. And now he's offering me to stay for 300 gold. So I'm going to stay, play some celebratory resting dance animation. And you can see that my health is restored and my gold amount was deducted, right? So why am I showing you all of this? Because it seems like a pretty daunting amount of gameplay that I have here, right? And I did it in a surprisingly small amount of time. And one of the main reasons why I was able to do all of this is because of StateTree. So one of the cool things about gameplay programming in Unreal is that if you know the right tools, you have an amazing resource multiplier where you can do some pretty amazing stuff with very minimal resources in very little time, right? I'm a big fan of stuff like Gameplay Ability System. I can do low-level C++ if I need to, if there's no other alternative to that, right? But one of the disadvantages of traditional programming tools, including GAS, is that they're not very good at representing finite state machines, right? Stuff, you can think of a state machine as something that has modes, right? Stuff like an NPC where he's moving, then he's talking, he's basically jumping from very discrete modes or states, one from the other, and you want to ignore a whole bunch of behaviors at a time, right? You don't want there to be any incongruences there because that's where you actually get bugs, right? So the cool thing about StateTree is that you get these really neat, organized, easy to design hierarchies. Let me show you something a little bit more complex. And you can see that these are actually some of the behaviors I have right now. This is my quest giver that asked for a potion, right? And you can basically just represent a lot of things like this, right? And this is all extensible. I actually had to build a lot of the functionality for interacting with the inventory, for doing dialogue, all of this. So this is if you're interested in seeing how I actually built all of this, then stand by for the next Titan release. It's probably coming in a couple of months, and you can actually have a pretty good primer of how to build something really cool with StateTree, right? Basically, if you can grab something in a way, if you can represent a gameplay behavior in a way where you have these discrete modes, right, and transitions between those modes, then StateTree is a tool that you at least want to consider because it can save you a lot of time and a lot of resources. Okay, this is not just for NPCs. when you're building gameplay, you're going to have stuff like UI, you're going to have stuff like dialogue systems, quest systems, game state flow, that all fall into this pattern. And so this is a very flexible tool, and you should definitely consider it for all of these cases. So now that I hopefully got your interest with this, I am just going to pass this to James, Patrick, and Jacob so they can give you the low-level technical details on how this entire thing works. So take it away, guys.
Yeah, so if you'll hop over to my screen, Dan.
Yes, let's do that. I also just want to say real quick, chat is loving this already. So this is awesome. The idea that you had a cube that damaged you as a hitbox is just too funny not to reiterate. That is hilarious. Yeah, your screen is back up.
All right. So I was just kind of go through a little bit of what some of the basics of StateTree are. So when you first open StateTree, can be very overwhelming, but hopefully this makes it a little bit more easier to understand. So this is a StateTree that I built as part of your first 60 minutes with StateTree, which I realized typically takes most people a lot longer than 60 minutes. I'm sorry, it was just supposed to be a catchy title. It wasn't an actual time frame of like, if you can do this in 60 minutes, you're great. If you do it in 60 minutes, you probably already know how to work with StateTree. But to begin with StateTree, it all comes to a schema. So StateTree itself kind of is just a hierarchical state machine schema, or how we make it do all the cool fun things that we see. So by default in the engine with the plugins, you have StateTree component schemas. So like a StateTree AI component or the StateTree component. These are set up for actor-based workflows. There's also a mass StateTree schema, as well as things like gameplay cameras now. The gameplay interaction system has a gameplay, or plugin rather, has its own schema. But schema is kind of how we set what data should always be available, like for a specific use case in our of using our StateTree. So like in an AI world, we want our AI StateTree to always be able to access the AI controller, the controlled pawn that we're kind of moving around with our AI controller. So we have those included as our AI controller class and our context actor class. You can use this with non-AI controllers by using the regular StateTree component. So you can put this on all kinds of things. It can be a cube that literally flies around in the world as like target practice. Like you can have it pop up and go back down as it's going behind various obstacles. You don't have to have it be an AI. It can run without an actual AI controller on it. But yeah, so we set all this stuff up. It's data that we have there. You can extend this with your own custom schemas. So you can extend this, add in data that you want. There's just other places in code where you kind of need to then link up what data you're pulling in and where it's supposed to gather said data. And then you'll notice right below it, we put in our context. So these are like the variables that are always available inside of our StateTree. They can be bound to automatically by setting like various task parameters as a context parameter, and it will look inside the actual context class to see if one exists, so it will pull the closest thing it can find. Beyond that, we've got so the main thing you're looking at, what are all these states that are going on? So this is our state hierarchy. So you have multiple things going on in here. You have leaf node states, which are kind of a state that doesn't have anything else below it. There's a few in here that are a hierarchical state, or like our intermediate states. So these are where we usually are always active if one of their leaves are currently running. So if we have our flee state is active, we actually are in the danger state being active as well as the root state. So all this can have its own tasks that are running. So we can have, like I need a task that continually runs even if I'm doing a bunch of these other states or behaviors. We can do that. We can also put things like conditions on there. So like I don't want to go into any of these states if I can't pass this inner condition of having a perceived hostile. So we kind of work in two ways. StateTree will by default always try to go into a leaf state. It won't usually go into an intermediate state, but you can change things. So we have selection behaviors for states, so you can do different things. So like we can do a try enter, which will mean it tries to go into that state, even if it has child states. So we'll go into there first, and then we can transition, and based on things that happen in our tasks or other parts of the state, we can then go into various child tasks. We have try select children in order. This is our default. It's the one that you'll see most of the time. They just go down the list of anything. It's a child state one. from top to bottom, seeing which one's there. You can also do things for at random. You can use utility scoring, so by trying to find the one with the highest utility, or random weighted by utility, or we can just say this state should only be used for transition. So as soon as this state gets selected, I just want you to run all of our transition logic to see which one we should head to. In addition to that, you also have types of states. So our basic is just a state. It exists. It is exactly this. It can contain tasks, it can contain transitions, it can have children. It's just our normal base node state. Below that, you have a group state, which has no tasks or anything on it. It just contains child states on top of it. You can also do a linked state, which allows you to link to another state inside of the state tree. So like we could have this state, link from one to the other. So like we could be into our idle state from assess surroundings. I don't want to set that up right now, but you can link to other parts, but it's within the same state tree that it's linked at. It allows you to kind of have like a simple place of like, here's a movement logic, like of moving to something, but I have that being used in combat and I have it being used if I'm not in combat. I still want to use the same movement without having to repeat those nodes all over the tree. You also have a linked asset state type. This will allow you to actually run a different state tree asset. So you can build a separate state tree and then inject it. It just needs to have the same schema to be able to run. But you can even set things for overrides and override different parameters for that state tree. This comes in quite handy. We've used it in various other projects. But if you're familiar with behavior tree, this is like the run behavior nodes in behavior tree. Allows you to just kind of set another one, but this is the state tree version of it. So if you're looking for like, how do I do this? There's a run parallel tree task, but there's also a linked asset that you can choose from a state. And the last one is a subtree. And this is where the linked states come into play. A linked state links to a subtree. So you can set something up as the subtree that then gets linked into as you're going around. And as we had mentioned a little bit earlier, you can put parameters. So you can have parameters in two places. You can have parameters that belong on a state. So this state will always have access to the parameter, and if it has any children's state, they'll be able to access that parameter from their parent state. But when I'm out of this and into other parts of it, I don't have to worry about this parameter just always being around or set inside of a big global set of parameters. But you can also add in your own global parameters, which you can use to store all kinds of data for it. So you can write things back to here with an output task. So task output parameters can actually push back into these different parameters, or you can even use them with stuff like property refs to be able to get a reference to that property deeper down. We also have in inner conditions. So being able to say when we're doing transitions, when should I be able to pick this state is very useful, because I don't want to be in danger if I don't have anything around me that I know is hostile. So we can put in different conditions. You can create your own custom conditions. We do have various conditions that already exist, so you can have it be, comparing floats, comparing integers, names, checking if something's actually valid. So this way we know I want to go into here first. And as part of conditions, you can also then put in a required event to enter. So a state tree event will have a gameplay tag, so you can set them up of how you would like these to be. So I can set what tags I would like to have. It also has an optional payload. So this is just a struct that you can include with it. So you can get, perception update info. Like I want to know, what did I just perceive that I should be hopping into here with? And I want to make sure that this exists. If we don't, we'll push out of here and we won't go into this state because we don't have the required event. And by setting the required event, you can actually bind to this event in your task. So you can actually pull data out of that event to be able to use inside of your own tasks. And once again, you don't have to have an event for a condition to work. It's just there in case you would like to have it. We also do some things with utility. So I mentioned earlier that you can select children by utility. So you can add in weights for states and then use the try select with utility. And add in various things of how you want that to look. So we have a float input that creates its own response curve, and you can adjust parts of this curve to be higher and lower, or if you just want it to be, a linear thing going through, and you can bind in from something of where you would like it to pull this information from, because usually it's not just a constant of like, I want this to always be 0.1. Maybe you have a backup that's always valid just so that we can choose something. But you can say like, hey, I want to do this. Like, what's my hunger level of a character if I want to go eat something? I don't want to go eat if I just ate. So you can put something in here like that. So you can be like, okay, at this point in the curve, it should be scoring it at a 0. But just general utility things. If you're familiar with utility AI, this is a way to be able to use it. They're called considerations, I believe, Jacob, inside of the engine. Utility consider. Okay, yes. I was like, make sure I'm not making that one up. They're called considerations. You can create your own. We have a few that are available right now that you can just use, but you can create your own utility consideration to be able to add scoring into it. And then one of the main things that everybody likes to see is tasks. What do we actually do inside of our states? So this is where you add various behaviors in. So you can have custom tasks like I have here for like in my own run EQS task. I have a move to task, or you can use ones that are built into the engine. So like we have a delay task, which just does what it says. It runs for an X amount of time, and then it will finish as a succeed and complete the states out. Your tasks can also work to transition things. So when a task completes, we can then run in transition logic. You can also choose which task should be part of the consideration for whether the state has completed by just clicking the button here to the left of the name. So plus means we're including it, minus we don't, whatever this one comes back has, it doesn't go into there unless it's a failed task. So we'll wait for these, and you can even change how things should go. So should we wait for all of them to finish and be proper, all of them to finish and be ready to go, or should any of them come through and immediately trigger it? Any was the way that it ran for quite a while. I believe it's still the default. So any task that finishes will trigger transitions. It can be very confusing when you're first setting it up because you can have a task that would accidentally call finish that's like in an intermediate state that would immediately finish whatever a child's doing. So you can change that to all, or you can just, if I don't care about what this does, I can just uncheck it. I don't need to know if this one fails or succeeds. It's just not part of my actual transition logic. Now we get into the cool part of tasks, being able to run our behaviors, of being able to bind properties to them. So here's where we can do things like our context actor or our context AI control in this example. So we have a task that takes an AI controller in. It's a context one, so it automatically tries to grab from our context parameters. That's what the chain here is it automatically linked it. But if say, usually I always want it to be a context, but I have a very special scenario where I want it to be a very specific one for this one task, I can always set it to another parameter. I can set it to something else to bind into. So this way we're not using the one from our context. But I don't have to change anything else in the task. It can be used multiple times. You also have output parameters. So output parameters are like what a task does and then spits out a result. You can now bind these to a parameter inside of your state tree. So this can bind to a state tree parameter that's on the state. So I have an EQS result parameter I can bind to there, or I can even promote it to a global parameter and bind it out on my larger state tree. So it's even above, and so it's available for everything in the state tree, not just this state or child states. We also have another special category for our properties that's an input. An input is something is required to be bound. So if you go to compile your state tree and an input is not bound, we will fail the compilation and then tell you like what state, what task is expecting something to be bound to it. So this way, like you have an idea of I clicked it, why didn't everything compile? It'll tell you like this one needs to be bound so you can go in and do it. This means that this should always be valid. I should always be able to get to this inside of my task. Or you can have things that are optional to be bound. Like I don't have to have this put in, but I would like to have it, such as a move to location. Like in a move to task, I feel like you'd probably always want that to be set, but maybe it's not as important that it's always set. I just want to be able to bind to it occasionally. And then you can click to bind, which this is how it would usually look. You can go in here and look at like an actor, get different parts of it. Or you can use our property functions, which allow you to kind of do a little bit of logic on what's happening. So I can say I want to use a property function for get actor location. So instead of being able to provide the location directly, I can go grab the actor that I want to use to be able to use its location, which it'll automatically do that. And you can create your own state tree property functions. We have them that exist for other things, such as floats and integers. You can do logic with them, so and or not. We have a lot of things that are kind of built in, but you can also create your own to be able to kind of gather data. So this way you don't have to have very specialized tasks that always get this data from a very, complex thing of an actor or something in your hierarchy. All right. And then, so we have at the end, we have transitions. Let's see. We have transitions that go through. So when a state completes, succeeds, fails, we then want to be able to go to another state so I can continue my logic going. So you can add in your transitions. It's just a button to click to add one in. And then you can say how we want them to work. So you can have multiple triggers for what this does. So we have on state completed, which succeed or fail. We can take this transition. We can also do state succeeded or state failed in specifically. So if a task fails or succeeds, we can go for that specific transition. There's also ones for on tick. You probably don't want to use on tick as much just because it will go every single time to try to see if that one is still valid. You can use StateTree events, which this allows you to once again use the required events. So you can send in a gameplay tag with a payload and then say this must be present for me to take this transition. So you could set in like, hey, when I get something come in while I'm in calm, I want it to immediately shoot me over to danger based on this event coming in. Or you can use our new delegate system where you can actually bind to the delegate of another StateTree state or task rather that will then only trigger when that delegate is triggered from inside the task. It'll call, I believe it's trigger delegates, and it will send this out automatically, and then we can have it choose where we want to go. The delegate system is a little bit new. I'm using it here on this other state, which is just a find and move to berries. So instead of having two states where we would have one that runs an EQS and one that waits for the EQS result, I can have an EQS or I can have a query dispatcher, so our StateTree delegate dispatcher. So delegates come in two flavors. We have a dispatcher and a listener. So dispatcher is the one that's going to send the delegate broadcast out, and then our listener is the one that we can bind to that specific delegate. So on our StateTree move to wait for delegate, it actually has a binding to go into the StateTree EQS task and then look for when this is finished. So this way I can start my EQS task while I'm in this state, and then I won't start moving until that finishes. So if you do have an EQS task that's a bit more expensive, it'll kind of wait a little bit, but this way like you don't have to try to jump between multiple states and have more and more states plugging in just because you're trying to go from one to the other and just waiting on a specific task. You could also, optionally, have a dispatcher for if this completes successfully, I would like to go do something, and I could put that in as a transition. So I could put it in as a on delegate and then bind to my EQS delegate and have a one that's a specific EQS query result, valid or an invalid one, and then choose which one of those. So this way I could have different behavior based on if the environment query succeeded or failed. And then, so then as our environment query ran, the task would call into the dispatcher, the correct one, and then we could go down and set the rules for where they go. So one of the other important parts of a transition is where do I go when this happens? So this is kind of where you set up of, I want to be able to jump from one to the other. So if I'm on find to move to berries, if I get a very specific one, maybe I want to go to grays instead of having this also move to the berries. Or maybe I want it to go to a wonder target. But I can set all these in here as I go along, and this will only happen when this delegate dispatcher gets called. So we'll hit the listener and then be able to move on with that. Let's see. So yeah, I believe that's most of our main concepts for StateTree. Once again, if you have questions or if you may have missed something or spoke over it too quickly, do let us know. We have a very good breakdown of this in your first 60 minutes with StateTree towards the top of the article that kind of goes into what all these things do, where they're at, how to be able to use them. One of the other things I will mention real quick, I just was looking through that and see it, is evaluators. So we have evaluators. They used to be something we used in StateTree over here on the left. So we would use evaluators to be able to get external data into our StateTree. So these kind of would run for the lifetime of our StateTree. So usually they'd be like on begin, we would do something to find data. So we would gather things from either like our context actor class to be able to put into a parameter to be able to bind to. But now you can also then just add tasks, global tasks to your StateTree. So this is a task that will run forever while your StateTree is going. We've been moving from evaluators to global tasks. So if you're needing to get that kind of data, put it in a task. It's just a regular StateTree task, but you can put it in here, then have on interstate, I want to do something very specific of being able to update something back into it. And then you can bind from these things that have parameters. You can either push it into the global parameters, or you can just have it as a binding target for everything else inside of your tree. So this way, any of our states will be able to find this as long as it has a valid parameter and they match the types. All right, and with that, I will send it over to Patrick to kind of dive into some of the black box things that aren't as easy to see from the editor.
There's a lot of it. Thank you, James. So we're going to talk about everything that's happening under the hood that you don't really see. And I'm mostly talking right now to the expert designer, the technical designer, or the programmer, but it's going to be useful information for pretty much everyone. So we want to talk first about how do we tick the state tree. One thing to be sure that everyone understands is if I'm inside the state green, I'm also inside the state root, and I'm also inside the global context. So when I'm ticking, I'm going to tick everything inside the global, also ticking everything that's inside root. Right now, root is empty, and everything inside the state green. So the order is always from top to bottom. We're going to take everything that's global, then going down the tree or wherever is the active state. So let's say blue is my active state. I'm going to take all the globals, all the roots, then that render selector, then everything is inside state blue. We're only going to take the task. So there's nothing special taking on the state itself. What we're looking at are the states. And of course, the evaluators. In that regard, evaluator is a bit different, and we're going to see it when we're going to talk about the schedule tick. We're going to take the tasks that are not completed. So let's say I started, I'm transitioned to state blue. We did the evaluator, the global task, root, random selector, state blue. We did this task that is going to wait for, I believe, 2 seconds. And then I'm going to do this task called color change, which is going to change the color of material. If that task completes, and I need to tick and tick and tick again, since that task has already been completed, it will not get ticked again. The task gets ticked until they are completed. Then, like James said, we have any and all, and the rule are the same. It doesn't matter if you're any or all. The rule are exactly the same. It's the only difference is for the completion is to say when the state completed. It doesn't matter for the ticking loop. When we are ticking, before ticking, we're always going to run the bindings before ticking a specific state, a specific evaluator, or a specific task. So let's say we're starting our new frame. We want to tick that evaluator. Before ticking the evaluator, we're going to update all the bindings. This one have context, which is automatically bound, and we're going to update it, and that's it. Then we're going to run that evaluator. Same thing with that global task. We're going to run the bindings, then the task. Binding, there's no task, nothing. This one had a task. We're going to run the bindings, then the task. And then, again, the binding for all of those, then run the task itself. If the task is already completed, we don't need to run the bind. It's not going to get tick. If it's not going to get tick, we're not going to run the bindings. Right? As you might imagine, we don't want to tick because ticking costs a bit of CPU, a bit of process, and we would like to prevent ticking if possible. So there's a lot of small features that big feature is called schedule tick. And what's happening is under the hood, we calculate if we need to tick the StateTree for that specific instance. And if we do, we're going to tick it. And it's possible also that we're going to delay the tick for some frames, or we want to wait until an event occurs or some task finish to start ticking again. So the basic is if your task have a tick function, this one does not, then it will not get tick. And if it doesn't need to get tick, and if none of the tasks inside your StateTree need to tick, then it will not get tick, and you will not know about it. How to know about it? There's that flag here. If you check it out, and your task, can I do it live? That would be awesome if it works live. If it doesn't, I'm going to look stupid. But let's try. I have a tick function now. Compile, save, and okay, like it should work. Yeah, it did. Okay, I have this tick icon here showing me that this specific state will tick. Be careful about it, and all of the other one because they all use the same task out of it. So that's a good way for you to know whether it's going to get tick or not. On top of that, if you want, you can customize the tick rate for that specific state. And you can say, example, tick it every second or so. There's nothing magic here. It's not like I'm going to tick root, but not state green until I reach 1 second, and then I'm going to like this. It's going to try to do its best. And the rule is if it needs to tick, it will tick. And it's possible that you request 1 second, but something else somewhere requested a more frequent tick. You're just going to get tick more often. A good example of that is daily task. Daily task manually in C++, not the right window, Patrick, this one. Daily task. Manually in C++, when we enter the state, we say, this task, I want a custom tick rate for this task. I need to wait 2 seconds. So don't bother ticking for the next 2 seconds. So this tells the algorithm that this specific state would wish to have a custom tick rate of 2 seconds. But if something else wants to tick it, they'll tick it. And it's possible that I will get tick more often and I still need to check if it's not like magically that I put the custom tick rate of 2 seconds, that magically this tick will not get tick in 2 seconds. It's possible to get tick more often, depending on what's happening around with other state, other tasks. So I still need to check if my remaining time is F process is down to 0. Evaluators are not part of that ticking logic. So that's one pros for the evaluators compared to global tasks. If you have a task that fetch data and there's no logic inside of it to say you should not tick, it will tick every frame. And if it ticks every frame, it's going to tell the algorithm that it needs to tick every frame. So even though nothing else tick, if your global task need to tick, everything's going to get tick. One pros for the evaluators is they're not part of that scheduled tick algorithm. If you do not have, if you do have evaluators, they're not part of that algorithm. So other tasks, it's possible that it will never tick, and only when you're going to tick, it will going to evaluate the data. If you want a task that never tick, no matter there's not, it's possible to mark a task that is marked as not considered for scheduled tick, and it's a special flag that you can only set in C++, I believe. And then when you set this flag, this task will never be considered. So it's a good way to do an evaluator as a task. It just requires you to do more steps to make sure that it is done properly. Is it what I want to cover about ticking? I think so. Now we can talk about the transition. So if ticking goes from the top of the tree to the bottom of the tree, transition is the opposite. It goes from the bottom of the tree to the top of the tree. There's three categories of transitions. There's manual transition, so something that manually by code in your blueprint or C++ that you request, I want to transition to this state, and those are the ones that are evaluated first. They can be sorted by priorities. Somewhere there's priorities. Where's the priorities? Somewhere, wherever.
Change it to on event or tick.
Okay, yeah. Okay. Well, I'll change that later because I don't want to break my my demo. So after that, we do have. Let's do it because it's gonna be. we do have others. The next category is triggers. So triggers are tick, event, and delegate. On event is used when you are receiving an event from. It's generally used and should be used when it's something triggered from outside of the state tree. You're inside Blueprint, you have some logic, and you want to send an event to the state tree. You don't necessarily need to know which state is going to capture that event. You just want to send it to state tree, and state tree is going to manage that event. Contrary to delegate, delegate is I want this specific delegate from this specific task or this specific state. And when this specific delegate trigger, I want to run that transition. So those are the trigger category. Once again, they're gonna get triggered after the manual, and after the trigger, we're gonna run the completion. So either complete, succeed, or fail. Complete is I don't care if it's succeed or fail. If the state completed, trigger the transition. Succeed is if the state, if only and only if only the state succeed, and if fail is if only the state failed. In case you want different branch, in case your state succeed or fail. So the order is from run all the manual requests. If one is correct and accepted, we're going to run that transition. If none of them, then we're going to run the triggers that take the event delegate. And if none of them works, then we're going to run the completion, again, from bottom to top. And completion doesn't have any priorities. The logic of state tree makes sure there's always one state that's always valid. So we try to never get into a limbo state where you're stuck and nothing is running. To check if that occurs, there's a special loop inside the logic that runs 5 times. And 5 is just a magic number. I don't know why it's 5. Someone put 5 and it stuck. So what's going to happen is we're going to check 1 for transition. And if nothing occurs and we're stuck, we're going to try to go to root and try again from root and try to find a correct state from root. And again, so make sure again and again until we find a good state to stay. So again, let's say I wanted to go to blue from green to blue, and I'm not able to for whatever reason. Example, the condition doesn't work. I'm stuck. I need to do something instead of just reporting an error. Like we do if you look at the log, you'll see. But we want the game to crash. So what we're going to do, we're going to start from root and try to find another state that will fulfill that transition. We do have special cases, and that's stuff that I would like to look at. Right now, it's kind of complicated it can be complicated to follow all the different steps. When it's easy when I'm inside this state, and it's easy when this completes. I want to go specifically to this state. This logic is speak to itself. This is what I want to try. But there's that's more a bit complex, like this one, where it says try to go to root, but it's possible that you'll do something else. This one is also go directly to root. I'm specifically telling it. And this one is go to the next state, and it's possible that it's not able to do it, and it's possible there's other condition that may change that behavior. So those are a bit more complex to understand and follow. And here I have a great hard example to make it all work. So what we have here is one tree and a second tree. Like Jamie explained, this is a subtree. So a state can link to that subtree. When I'm going to transition to linked state, what's going to happen, we're going to follow the link. We're going to select sub3, and sub3 is going to select its children. In this case, it's going to be yellow. When we're going to a sub3, we call those three are different from this tree. I'm inside a second tree. When this tree completes, it's the same as saying this state completed. Whatever happened here, as soon as this state complete here, it's the same thing as saying this state completes. Following that logic, here we don't have any transition that says anything. I'm going to try to go to root, which says this is completed. I don't have any transition. Go to my parent. I don't have any transition. And this one now is considered complete. Since this one is completed, this one is also considered completed. Oh, and look, there's a transition on it that says it's completed. And if it's completed, go to random selector. And it's go up one level. And that's going to be the state which we're going to try to transition to. This specific sub3 logic can also happen when it's here, when it's a linked asset. Same logic. It's just that this tree is now represented into a different asset. If I'm going here, I have a different asset. Let's say this one completes. It's going to complete root. And if it would be linked to, it would complete this one, and that one would trigger the transition. Same thing also with run parallel. Run parallel is a special task that is able to run a link StateTree in parallel with the same information data that you have here, same context data. So when that tree would complete, it would complete that task, and that task would complete the state, and the transition would take effect. The way the transition are evaluated, and another right one, is a bit complex. And which state we're going to select is a bit complex. There's a lot of documentation. We try to put out documentation with different cases of what the transition is going to do. If you're a bit confused, try to read that. The best way I can tell you is you go up a level, and then you try to find a transition that would work for that. Now that we know that we're going to select the state, it doesn't mean that we're going to select this state. It's possible that based on the selection behavior, we're going to select a different state. So for example, when we start the game, we're going to start by selecting the root, and root wants to select something else, and you're going to try to select the child in order. So the next one we're going to try is state green, and state green is it's a final state. It's going to say, cool, try to select, I don't care, just select me. While we're doing that selection, we're going to evaluate the entry condition. So again, we start the game. We start selecting the root. We're going to check for the condition. I try to select the first child in order, and we're going to try this condition. If the condition fails, we're going to go back to where we were, and we're going to continue trying until we find a correct state. So if here I would have a condition that would always fails, or just fails on the condition, since root is try select children in order, it's going to try select a green. If it fails, it's going to try to select the next one. If that one fails, it was not able to select anything, And that's when we start doing the special logic where we try again and again until we find a state that's valid, because we do not want to be in a place where no state is selected. There's different type of selection behavior. I choose that one on purpose. This one is select children at random. So it's a throw of dice. If this one wins, we're going to try the enter condition. If possible, we're going to select it. If not, throw a dice again, and we're going to try to select the next one and try again the enter condition. And that logic continue. Doesn't matter if you're inside a linked asset, linked subtree. That logic follows. I'm going to start again. Root, enter condition. I'm going to try random selection. Linked asset, going to try the enter condition. I'm linked to what? Sub3, enter condition. This one is try select in order. I'm going to select StateTree. This one is a final one. That's the one I'm going to select. Once I've decided that I'm going to select a state, now the fun begins with the enter and exit state. First, I want to make sure I followed all my note. I did say everything that I wanted to say. Yeah, good. We decided that we wanted to go to a state. What we need to do is on exit every state that we were there before previously, that were active previously, and then call on enter on all the new states. But that can happen in different ways, and that also can be confusing. For simple cases, let's say I was in yellow and I want to go to orange. I was before the, okay. I'm just going to copy paste this state. It's going to be easier. Green 2, just to explain. Green, very green. I was in green and I want to go to very green. If you remember, the full path is the global, the root, and state green. Where I want to go next is state, the very green state, and the full path of the very green state is global, root, and very green. The green and very green share the same root and share the same global. Since they share the same global, those one will not get on exit and will not get on enter. They're already active. I don't need to reactivate them. So in this case, going from green to very green, I'm going to call on exit on green. And once all the on exits get called, then I'm going to call on enter on all the state. In this case, only one, very green. That is a very subtle thing here. Is because I went directly from state green to very green that I can say that. It's not the case if I was going through a transition through a complex path. Let's say here that I'm going to root, and by some logic, root decided to skip green and go to very green. Maybe because I have an enter condition that prevented it. If I'm inside green, I'm going to root, and root decides what you want to go to select, and it end up to very green. We went through root, and since we went through root to do that selection, root will receive an on enter. Even if it's the same root, it will receive an on enter. There's a special flag inside on enter that you can check to see if it's the same root or a new root. And this is called change or sustained state. So it is when it's a new state, a new root, it's going to get the flag changed. But when it's the same root, it's going to get the state sustained. Depending on what you're doing, it may be useful to know if you're re-entering the same state that was already activated or not. And that's why that flag exists. For subtrees or link trees, it's the same logic. We're going to, if I want to go to, let's delete very green. If I'm going to green to yellow, it's going to be the same logic. I'm going to do all the logic to find where I want to go. Then I know we're going to select state yellow. We're going to call onExit on state green. Since it's the same, let's change that to next state. Since I know that I'm going directly from state green to yellow, and I did not go through root this time, root is not implicated in the transition. The onEnter on root will not get called. I will receive onExit on state green, onEnter on random, onEnter on link, onEnter of the global of StateTree sub3, which doesn't exist in this case, the onEnter on sub3, and finally the onEnter on state yellow. I mentioned that the global of sub StateTree doesn't exist in this case because they're the same global. We're not going to call them because they're the same global for root and sub3. But they will be different if it is a link asset, and in that case, the global will get called. And that's it for the super big black magic stuff. Did I miss something? James, what do you think?
I believe you were very good on all that type of stuff. Yeah, thanks for breaking down exactly when exit state interstate gets called. I know that gets very confusing, especially as you're traversing complex trees.
And James, whenever people get confused, what they can do is they can just debug. So let's say a pi here, we can go to the debugger bottom, and the debugger in 5.8 has been moved, or 5.7, not sure, has been moved to the rewind debugger, which is open here. So if I start recording, you're going to see that I changed something to ticking, and now everything is ticking. Good job, Patrick. Example, should probably remove that tick. And something that we do not want to see. All of those tick, those are horrible, and we want to remove that from there. It's going to make my job way harder now, but you see here that when you click on a specific event, you see on a specific frame, you see everything that happened for that specific actor for that specific frame. So we try to tick the task, the global task, then we take the in which order we take them, etc. And and if we were in more, I'm gonna have no example. Good job. Here we have the linked asset, and that linked asset here in the debugger magically expanded to included the subtree here. And we can see also in transition what are the transitions that ran, in which order they ran. So it can also help people understand the logic and why their three behave that way. There's a nice feature that we didn't talk much about, which is parallel tree, which, like we said, this is mostly done for stuff that the basic example is animation. I have an upper body and a lower body. Those two things run at the same time through the same AI. And you can see it in the debugger as different entries. That can also be useful. You see that my parallel is here as a different tree. Let's go back to Seb.
Quick question for you, Patrick, before you pass it
Yes.
off. I just saw somebody in chat. How did you get to this debugger? If they're looking at their UI and they don't see it, what is the way to bring that up for them?
The easiest way is window debugger. It's going to pop up this one. You can open rewind debugger. Oh, come on, not this button. Move it on screen. And it's going to open this one for you. And let's say it was not open. You can always open it here. And if you have more than one instance of that actor, you'd be able to select which one you want the active one.
Perfect. Thanks so
One
much.
thing that is, since people ask that question, I imagine that people are not used to this view. We have a break on enter. So when you pi, and you start recording, if I can get recording going, whenever we're going to enter that state, the pi is going to stop. It's also a good way to, like right now, it's also a good way to just stop, analyze your actor, see what's going on, what are the variable values. To note that it doesn't break, it doesn't stop pi as soon as it enters the state. It will stop pi at the end of the frame. So the action already executed. Does that answer your question, Dan?
Yep, that was it.
Yes.
That was perfect. Thank you so much.
And for everybody on here, the rewind debugger is used for StateTree in 5.7 as well. We stopped the StateTree debugger for 5.7 to go into all the stuff for the rewind debugger. You can also get to it by going to in the main menu or main screen where you have the level open. You can go to tools and then debugging, and then there's one in there for the rewind debugger. So you can use rewind debugger and rewind debugger details.
Awesome. Thank you so much. I think you said Seb, maybe. Toss it back to you, Seb.
Sure, if you can share my screen. All right, so you listen to James and Patrick just go over the technical details of how this entire thing works. So what I want to do now is just go back to my Titan examples and show you how some of this is implemented in practice, right? So a fair disclaimer on this is that I am obviously not a StateTree engineer. So there are some of this stuff that I'm still learning. In fact, I'm learning as much as you are right now. Okay, so if I say something that is blatantly incorrect or against best practices, feel free to stop me at any point.
I will stop you, Seb.
Thanks. And in fact, I am going to apologize right away because if you can see my screen, I have a lot of unoptimized ticks over here that I have yet to disable. These are because these are using a lot of C++ implemented tasks, right? And I haven't disabled tick on the native tasks, so it just assumes that it's using tick even though it's not using it. All right.
Yeah, that's a good point, Sebastian. For Blueprint, this is detected automatically, but not for C++. You need to manually tell the task.
Exactly. So I need to go back to my example code and just disable a lot of properties on some of the class constructors for the tasks. Okay, so the first one that I wanted to show you here is basically the quest giver, the guy that was asking for a healing potion over here. And I think this is a good example of a simple branching dialog. So I want to walk you through it. So the first thing that I'm going to do here is I have an initialization state. And this one is basically running a few tasks that are creating the dialog window, ensuring that I have a player controller to read the input from, assigning it to the dialog window. And if anything goes wrong with these in any of these tasks, these are going to fail, right? And if any of these tasks fail, you can see that I have a few transitions set up. So in case we fail, this is something that I like to do on a lot of my state trees, just add a catch-all error state that I can break into, that I can just check over here in case something broke. Right, so because this is going to be a critical point, I can't really play dialogue if there's no dialogue window or player controller. Then it makes sense to just error out on this entire thing. Okay, so assuming that everything went correctly, which is hopefully going to be most of the time, I can start just doing state tree tasks to do stuff like activate the gameplay ability on my character that is going to make sure that they stay still. Hopefully in the future, they focus the target with the camera. The NPC rotates towards the target, and then we start playing the dialogue. And all of this is done through tasks. Basically, anything where your state tree wants to interact with the rest of Unreal is going to be done through tasks. So this is where you're going to do 90% of your state tree code, okay? So basically, this is something that I implemented on C++, but you can also do it on Blueprint. I'm going to show you some on Blueprint before. So I have my dialog pages over here, all of the dialogue. So on this first one, we just have some flavor text and introduction, and then I need to check for my inventory. So aside from just adding some dialogue over here, you can see that I have some transitions set up. So completed is going to be called when the last dialog node is closed. And then I have to check. So I am doing the same completed transition in order. So according to what Patrick said, they're going to execute top to bottom. And you can see that I have a condition here where I say if I have at least one potion in my inventory, then I am going to go into the has potion state. Otherwise, I'm just going to go into no potion, and I am going to end the dialogue and exit out of this tree, right? So once we get here, we play more text, and then we get to a player choice. And the way that we do it here in my task, I'm basically saying the UI that I expect two responses. So this is going to populate it with two buttons, one that says sure, one that says no way. And I am telling each one of these buttons what state tree event it's going to respond with. Okay, so I have response 1, response 2, just using generic names over here. And in this same state, I am listening for events, external event transitions. So basically, when I want something from outside of my state tree to interact with my state tree, 90% of the time, what I want to do is just use an event. So here, basically, I say response 1, just go to the next state, which is give the potion, subtract the money through a gameplay effect using gameplay ability system, and just exit. And if not, then I just default to the no potion, and it's the same as if I had before. So this is how I make a very simple branching dialog here. Probably not as organized as something like Twine as a dedicated interactive narrative tool. But you can see that it's readable and it actually works, and the editor is there. So I didn't have to code an entire dialog system editor into Unreal to get all of this to work. All right. So next thing that I wanted to show you is the follow waypoints. So these are my top level state trees. So you can see that these are actually composite behaviors. Okay. So in this one, I have a follow waypoints and talk behavior, right? So I'm going to have these two substates that are very specific, and they're going to be gated by entering conditions. Okay. So in this case, let me see. Yeah, you can see that I have a required event to enter on each one of these. And here I'm waiting for the movement data. And here I'm waiting for gameplay interaction from the player, right? You get close, you press the button, and the character talks, right? And one really cool thing about gameplay events is that you can actually specify a payload. So I can't just receive an event, but I can actually receive all of the data that I want, and I can pass it to my linked state tree or whatever else is going to do with this behavior, right? So you can see on my MVC over here that I actually have some instance editable properties here, like my waypoints. So in each one of these actors, if I want to set up my path, all I need to do is just add some nodes and specify things like, well, I want to move here, I want to move at this speed, I want to wait between this and this time, and maybe I want to play an animation montage once I get to that point, okay? And then I am just going to loop through all of these things. Same for simple dialogue. So for most flavor NPCs that have nothing to do with quests or shops or anything like that, basically all I want to do is just play a sequence of dialogue. So it makes sense to just have them on available for the designers here. So I just have this information. And when I transition into these states, I can just use this struct as the payload, and I can pass it to the subtree. So you can see here that I'm actually binding to the enter events payload and just passing all of this to the subtree. Okay. So another really cool thing that we can do here, right? You can see that this is a linked state tree. So that means that I don't need to implement. I can basically reuse this behavior, and I can override it with this specific information that I want here, right? Same for loop waypoints. I can just use this, and I can pass the waypoint data, and that way I can maintain this, and I can start building a reusable library of behaviors that I can just share between projects or maintain a little bit more easily instead of just having to redo a whole bunch of work every single time. Okay. And next thing that I wanted to show you is an example of state tree tasks. So you can do this in either C++ or Blueprint. I'm actually using both here. So if you want a state tree task over here, you go into Blueprint class. I'm going to create a Blueprint class. And I'm going to look at state tree task Blueprint base, and then I can just start overriding some of the functions. Like enter state, exit state, or stuff like that. So one thing that is very common when you actually do enter, exit, and tick, I don't think tick in this case, but at least enter and exit is something that Patrick mentioned, and it's that you want to check the transition change type, if it's changed or sustained. Because a lot of the time you just care about executing this logic if there's an actual state transition change instead of just having a sustain for a part of the branch. So this way you can minimize a lot of extra calls to enter state. I know that there were some questions that we had before that were asking about this specifically. So that it was a good pick.
It could be easier, Sebastian. I'm going to teach you something, Sebastian. Click on the class default.
Class defaults. There we go.
There's a flag on the right called should state change on reselect.
Oh, here we go. So this is actually a way to...
You don't need that logic now.
This is great. So this is not going to be for the final version. But in any case, this may be useful in some cases where you actually want to process this or branch on this logic. So this is how you would actually do it in this point. Like I said, there's a lot of tricks here. I'm still learning, so I learned something new. Okay. So next thing, this can be as simple or as complex as you want. These are basically going to be the main ways where you interact with the game world from within StateTree. Okay, so quick example, this is my waypoint logic. And something that is interesting here is that I'm actually doing a for each using a StateTree task over here. So this task is actually going to do all of the walking through the waypoint list for my path and just outputting this so StateTree can run the environment query and move to the waypoint and do a whole bunch of other stuff there, playing the animations, basically doing all of the top level stuff. Okay, so this is how you would do something like this. So ignore this part. We know that there's better ways to do it. So at top, I'm basically just handling a few cases for what happens if I'm just using an empty list or something like that. So I want to make sure that I fail the task to keep it consistent. And this is basically I just get the node from here and I start outputting this to different variables. So within gameplay tasks, within StateTree tasks, you actually have properties that you can that can basically read in or output information. So you can see that I'm outputting the actor, the wait time, the montage, so they can be consumed by everything else, and I'm binding them to global parameters here, so they're accessible to this entire tree. Right. And one cool thing that I'm doing here is I'm actually doing a double binding on the same property. So I can't do an in and an out property at the same time that doesn't exist in StateTree yet. But I can do an in binding and an out binding over the same parameter. So that's why I have an in waypoint index, which is my input value, the before value. And over here, I'm incrementing it and I'm outputting it to an out value that gets bound into the parameter. So one neat trick that I learned the other day. And finally, the last one that I wanted to show you is the shop logic. And again, this is an example of stuff that can probably be optimized a little bit better. So and this is probably something that you want to look out for when you're designing state trees, because there's actually ways to make your job a little bit easier, okay? So you can see here that I have pretty much the same logic after I do my stock selection, what I want to buy. And I'm going to have the same pattern for the health potion, the vitality elixir, and the poison. Okay, so in all of these, I'm going to check if I have enough gold. I am then going to present do I want to buy or not dialogue. And then I am going to just apply the result through the inventory. Okay. So this is the kind of stuff that this is the kind of place where I would be looking to implement something like a subtree or a linked state tree and pass parameters here, because if I just take some of these parameters that I have here, like, for example, the dialogue nodes, the gameplay effects that I apply, and all of this is basically going to be the same thing. So it doesn't make sense to just repeat it 3 times and expose myself 3 times for human error. So this is the kind of stuff that you should be looking into, right? If there's stuff that you can reuse, there's stuff that you can automate through parameters and other stuff, you should probably be looking for these opportunities to make your state tree logic a little bit simpler, okay? All right, so this is what I got for you. I believe that, Patrick, I don't know if you wanted to just go over a few other things.
Yeah, I would like to go talk about how the data is managed internally. But first, thank you, Sebastian, for the demo.
Sure
I
thing.
love looking at people and how they use the tool and how, like, just all the demonstration. Like my brain was working, thinking about how we can improve all those workflow and be better and produce a better tool. So thanks for that, Seb.
Perfect.
Then we can show my
Patrick, right?
screen if you
Yep.
wish. We
You're
know
up.
in the community there's a lot of questions about how the data is managed and what's the instance and what's the template data and all that. So we would like to talk a bit about it. This session is more dedicated for programmer, an engineer, but it's good information for everyone. One of the good thing about StateTree is we're trying to be memory performance, like really trying to get all the CPU as we can. So the data is really it's patch and is sequential in memory, which means that when we're taking the StateTree, we're not looking back and forth to get data. The data already in cache, and we can process the task pretty much really quick. But to do that, we need to manage the data in some ways, and that's what I would like to explain right now. So if you see here on the left, there's a lot of different type of data that is used. I'm not going to go through all of them, but the more important one. What people get often confused is what's the instance data and what's the template data. What's the data from that come from StateTree itself? The easiest way to see it is when I have a task, I may have some data that come with that task. But the task itself is reused for every instance of that StateTree. So if I have 1,000 actors, I'm going to have one and only one template data that is used. But it's possible that I'm going to have some data that need to change for each of those actors. And that's what we call instance data. So for every instance of my actors, I'm going to have an instance of that struct, but only one instance for that StateTree that exists in memory. This is great for stuff that is read-only, because if you change it, you're pretty much going to change it for every instance of your StateTree. Everyone is using it, and often it's not what we want. We want to be able to change it for this specific instance of that specific actors. We mentioned previously with James that we have inputs, context, and output categories. Those are just names. This one, like, you could put anything you want. You just do a bit more extra. Input is force you at compile time. Context will try to automatically match it for you from the context data. And output force you to have a binding back to some other data. But by convention, we put parameters when we need to. How do we define an instance? You need to do two things. First, you should define your struct or your UObject. You define your type here, and you return the way to construct the definition of your instance data. And everything else is managed internally. So what's happening when we select a state is every time we call on exit, from that buffer that is sequential in memory, that's continuous in memory, we're going to remove all the instance data from that state. And then when we're going to enter on other state, we're going to append that instance data to that buffer, which means that buffer grows and shrink depending on what you're using at that moment. So one of the advantage of using StateTree is you're only paying for what you're using at the moment. It use less memory, it make it more efficient. And that's one of the reasons we're able to get a lot of NPCs, or a lot of, if you look at the name of the project I'm looking for, CDPR, Red Project, we did a demo with Silver, not Silver, what's the name?
Witcher 4.
Witcher 4, thank you! That's one of the reasons we're able to do that demo with that many amount of NPCs, that we're making sure that we're only utilizing what we need to utilize, and everything is packed in memory, and we're able to quickly go over the NPCs.
Yes, and Patrick, you can also see that data in the statistics in the state tree itself
Correct.
by going to the window, and then statistics. It shows what the worst case is and where your data is kind of ending up at. So you can see more details about all the data you have and what it's taking up for an individual state tree.
So thank you, James. So we talk about that buffer, and that buffer is constituted from different type of data. And that's the type of data that we're constraining. That's the type of data that we have here. So we have the context data, we have the global parameters, the global instance of all those data. Each state contains some task, and those tasks may have instance data. So those constitute the buffer, and like I said, it grows and it shrinks. To know as a designer, to know exactly where the data come from doesn't really matter. It's more a way quickly for us to be able to access the data instead of going and finding the correct data in that buffer. Since we have a lot of type, we can easily go and jump directly to the correct location in that buffer to go get the data that we need.
I want to quickly add, like for template data and instance data, for special types like state tree delegates and property reference, they use bindings, but they're special types, and you can put them on the template data. It's an optimization we did a while back.
So as an optimization, Darren, you're saying that we can put a state tree
reference, state tree property reference. Sorry.
Okay, property property and delegate
Yeah.
listener at
Yeah. Don't have to be on the instance data. Yeah.
Thank you. So we do have instance data, and instance data, like we said, are per instance of those actors used at StateTree. We also have share instance data, and those are used for condition, utility consideration, or function bindings. We try to get away from that type, mainly because we have a multi-threaded issue, and it's with multi-threaded schema, they tend to use way more memory than we expect. Instead, what we're trying to use instead is the evaluation scope, which would create, when you need the data, we create it and destroy it immediately on the memory stack. We also have execution runtime data. This is an example here, and it looks similar to instance data, the way you define it. It's just a different function. And what it is from the first time you start your logic, through the logic until you stop your logic, that data will stay valid and stay there. So you can come in and out of the task or the state multiple times, and that data will always be valid and will never be destroyed or reinitialized. Contrary to the instance data, every time you re-enter a new state, not a sustained like we talked previously, a new change state, the data is created or destroyed. Not the case for execution runtime. How do I access those? So for template, this is read-only. I can read it. I cannot modify it. The instance data, I go and get it. For runtime data, same logic, just different function. We also have another category called external. And external data it's not my favorite, but it's used mainly in mass. It allows you to get data from a specific context, which could be useful when you're in multi-threaded context and you know the context you're in and you know where to get the specific object from that context. So the way it's set up is the schema knows about that information. You specify on your task that you need that specific type of data. You link it and you say, I need it. And at runtime, you can go and access it. And the way it works, it will go as the context, go get me that information. And it's not saved internally, it's served externally. So that's why it's called external data. Is there any other type of data we want to talk about? There's stuff like event data. They're all like, again, for us to be able to manage directly, you don't need to know all those types. Same thing with external global data. It's something more stuff internally. Like I said, they're all not needed. And why we have instance global data and instance data object, it's for GC reasons. Nothing else. Optimization. There's not really important to know why there's a difference as a user. James, do you think we cover it before we go to async? Does it sound good?
One quick question before you hop over here. So runtime data it's instance based, just like our instance data, right? It still exists when we go in and out. So you can feel free to change it. It doesn't change for every single instance of the task that's running.
Correct. If I have 100 actors, I will have 100 runtime data, and that runtime data stay valid through the duration of your the life of the actor.
All right. Yep. That's what I was thinking, but I wanted to make sure for everybody else as well that we did keep that as an instance data. It's just still there after we go out of scope.
What I really like about your comment is this is all stuff that it's visible in C++. You can do it in C++, but in Blueprint, the only thing you have is instance data, and the instance data is your blueprint. Those are your instance data you're seeing in your task. So here, there's no way to mess it up in Blueprint or do extra work. There's no way. So those are your instance data. So as a designer, you don't need to worry about all of that. If you're using Blueprint, you're just using instance data. That's it. Now we'd like to talk about async work. We do not like ticking. And the best way of not ticking is not looking at Sebastian examples. So since that data buffer grows and shrink as you move in and out, there's no guarantee that the data you're looking for will be valid. So if you want to request to do something in a callback, let's say you're waiting for an object to be loaded in memory, or you have an EQS trigger, or you're doing UI and you're waiting for a button click. You cannot register yourself to a delegate and expect it to work. It will crash, and it will not crash nicely. It will crash like randomly in some part of the memory. Like you're playing your animation and then all of a sudden your animation twitch and you're like, what the hell is going on? That's the type of stuff looking for. Don't do that. That is bad. So don't do any of those. Don't capture this. Don't capture the execution context. Don't capture the instance data. This is all bad stuff. That's why we created weak context for you. And what the weak context, you can capture the weak context. And when you're ready, you can transform a weak context to a strong context, similar to a weak pointer and a share pointer in C++. So you can convert your weak to a strong. And when you have your strong, then you can test if it's still valid. Did I change state? Did the task completed by something else in the meantime? Was the actor GC? Did the actor stop the logic? This tests all of that for you. And once that's valid, then you can do your work. So on the weak context, there's a finished task. And this is just a shortcut to do exactly this long form. So if you're lazy, this is fine. Creating what it's going to do is going to create a strong inside and call exactly the same stuff. So if you need to do more than one stuff, use the long form, because you don't need to create more than one strong. Because if you do this, you're going to create 5 strong. It's a bit costly. If you're going to do more than one stuff, use a strong. That's valid. From your strong context, you can, let's move around. You can access your instance data and you can modify that instance data. And since you say you're strong and you know your strong is valid, let's move the code because I know the context is valid. I can access instance data, I can modify that instance data. One thing that we do not add right now is, yes, we set the output, but if there was a binding on that output, that binding will not execute. And that something is missing, and we're looking into solution to find what could be done. Example of other stuff we should not do. This part is bad. Don't do it. Can I zoom less? I used a strong to get the data. Patrick said it was good. That's good data. Yes, but right after that, you'd say bye-bye, my strong context. And there's no guarantee after that what's happening with your data. Don't do it. Here, you're touching stuff you're not supposed to. As long as you have a strong context, you're good. All of that. So this is the good way to do it. As you mentioned, this is not thread safe. Meaning that if I want to have a parallel for, I'm going to start 4 thread, and that 4 thread going to access the same data. It's going to access the data. I don't have any locking mechanism inside of it. So yes, the data is safe. Yes, the data will not get GC garbage collected while I'm here, but it doesn't mean that it's thread safe. Just the data will be valid while I'm here. So we're not giving you any mechanism to make it thread safe. If you need to make it thread safe, you're responsible to put a lock here, or mutex, or an atomic, or whatever needs to be done here. This is bad. Don't do it. You put the correct locking mechanism.
If you hit a risk condition, it will tell you though. It will tell you there's a risk condition detected.
We'll try to tell you, but you're correct.
Yeah.
You are able to read. 2 thread can read the data. That is valid. And you will not get that warning that Jacob mentioned. But 2 writer or reader and a writer, we'll try to give you a warning about it. That's what I wanted to talk about. I think we're good. I think we did good. I think we covered a lot of stuff. And more easy, more complex, more everything. A bit of everything.
No, absolutely. This was awesome. The presentation was really great. The content was really great. Like I follow it along, right? And I'm not inherently in the programming side. I'm an artist by trade. So this was fantastic. Thank you all so much for putting this together and coming on to do this. We've gathered quite a few questions that we can throw your way. But before I did that, I wanted to make sure that we covered everything that we wanted to cover here. There wasn't any extraneous things left untouched. It sounds like we could be here for hours, right? There's plenty to cover here, but for the sake of the demonstration, was there any other things we wanted to touch on?
I think we're good. If you have any questions from the community, would like to hear and answer them.
Perfect. We actually have quite a few. We'll try to rapid fire these the best we can, but we'll see how we do. So first off, what is the current status for mass state trees when it comes to multi-threading? Can they already be safely executed in background threads?
James, want to answer?
I'll answer this. So yes, mass state tree is thread safe. Like the core tech is thread safe. So you can there's an option that you have to opt into. So you go into project settings, then into the mass state tree module at the bottom in the plugins. You expand that out, and there's a section there that says process entities in parallel with a checkbox. Enable it, and you can start running in parallel. With that said, it is up to you to make sure that your tasks in StateTree are thread safe if you're going to run in parallel. We don't have anything on it that just automatically makes sure that they're all thread safe in mass StateTree. So that would be on you to make sure that you're not writing to the same place using proper locks. But it is available there. We are working on a big thing for mass and for improvement that's a processor change for how we're going to be processing data. Hopefully landing here really soon, but should be in for 5.8. That, I mean, right now we're seeing double frame rate improvements for city sample with no changes to the processors, just changing how the underlying hood works. So yes, going wide on state tree or mass is supported out of the box. And in like 5.6. Before 5.6, I don't think the option was there. So if you're on an early version, you may not see it, but I believe it is in 5.6.
Awesome. Awesome. Another question we have was, what's a good way to create a state tree that manages the interactions between multiple actors? One could create a custom context/schema, but usually the content is just one actor or controller, and the tasks that are getting data from the other context can't be reused in a state with a different context. That was a lot.
There's a lot. The easiest, like, yes, a state tree can manage more than one actors. Sebastian demos Python did it. The easiest way, I really like new schema when you have different tech or you're trying to support different stuff. But a new schema is hard to create. It's not easy. Maybe something we need to improve on our side. But besides schema, the nice way about schema is you can enforce the context data, you can enforce the data, and you make sure the data is always valid. But beside that, you can always create your own, you can reuse an existing schema, and you can expose an array of actors or an array of objects via the global parameters and reuse and set it from Blueprint or set it from elsewhere. You can also send event from Blueprint to that through that state tree, telling it that there's new actors, there's stuff that changed. And so the array of actors did not magically change. If you tell state tree that, oh, something new happened, I sent you the event, new actor, or I'm going to remove an actor, and you send that. But I feel that context is the easiest way to do it.
Perfect. Perfect. Another one we had is, what's the best approach to achieve the closest level of abstraction that a blackboard provides when using StateTree?
The easiest answer is don't use a blackboard. I understand that people like Blackboard because that's how they used to work with other tech, and they like that it's easy, that's all the data is always there. If that's what you want, you can always put everything in your global parameters, or you can create a user-defined struct in Unreal as a different asset and use that user-defined struct as a variable in your global parameters and reusing that struct. There's always a pattern that people can follow. We remember when we talked about growing and resizing that buffer in the data, we want that buffer to be as small as possible. Less data in that buffer means less memory swap, less memory use, less cache miss, faster processing. And the fact that if we have all your data available all the time, go against that, and that's why we're probably never going to put anything like a blackboard directly inside StateTree. But if that's what people like and that's what they want to do, go ahead and do it manually via user-defined struct.
Great. One of the other questions we had here was evaluators versus global tasks. When should you prefer one over the other?
It's about 5.4. You should always prefer global task. Yes. I'll say evaluation still exists so that we can, keep everything going so you won't have a problem or a failure to compile, but everything should go to a global task now. If you're in anything past 5.4, use a global task. It does everything that an evaluator can do and has a little bit more functionality to it.
Just make sure it doesn't tick because it's an evaluator, it should not tick. So there's a special flag in C++.
Great. This is more of like a broad question, but when would you choose behavior trees versus state trees? Since there's a lot of similarity in what they do.
State trees are tools that can be used on different, like behavior trees was really directed for AI. And state tree is more large, looking at not just for AI, but also, like we said, camera, animation, etc. So that's one advantage. But I would say it depends on your team, it depends on your project. If you feel comfortable using, you did behavior tree all your life and you're starting a new project, why change? We will not continue supporting behavior tree in the future. Did I say it correctly? We will not add new feature to behavior tree in the future.
Yes, behavior trees in a maintenance mode, so no new developments going. Find bugs in it. We are still trying to fix bugs as they come through, but yeah, all of our new development, new features is all focused on StateTree, has been for a little while. I'll say, and Patrick hit the nail on the head. If you're familiar with behavior trees and that's the best tool that you have to be able to do it, behavior trees are still valid. You can use them. If you're looking at trying something new or wanting to go with the things that's going to have new features and everything coming for it, definitely move towards StateTree. And as Patrick has also mentioned, StateTree is very performance focused, trying to maximize, how much we can use in memory, or I guess minimize in this case of how much memory we're using on each thing.
Right. Yeah, kind of piggybacking off of this, based off of this demo alone, but also some of the things you mentioned, is this can be used for a kind of a wide variety of things, right? Like it seems like it's pretty versatile. For someone who's not familiar with StateTree or is just getting into it and trying to think of use cases, is there sort of like a North Star to kind of follow of just like when it makes sense to use StateTree versus maybe just like general Blueprint or C++ code for some of these features? Like what is the best guideline there?
I can take that one. Yeah. So C++ code is going to be generically useful, right? But if you are trying to do state machine code in C++ or in Blueprint or in any pretty much any programming language, basically what you're the point where you should start considering StateTree is, well, am I writing code where I basically have to use a lot of switches or a lot of ifs? If I am in this specific condition space, if I am talking to a character, then do this. If I am walking, then do this. If I am taking damage, then do this other thing. That's the kind of pattern where you want to start considering state machine, in this case, StateTree, right? That in games happens a lot, right? It's not just AI. Like everyone said, there's a lot of use cases. Camera makes sense for that. Animation makes sense for that. I mean, animation blueprints already have state machine built into that for precisely that reason, right? So it's a very useful pattern to have. And this is one of the reasons why I'm recommending everyone to check it out, because this is going to have a lot of usefulness throughout your career as a programmer in Unreal, right? There is a lot of use cases, and you're going to find more as you progress.
Yeah. I'm an environment artist by trade. I haven't done a whole lot of programming in my past, but in the past year or so, starting last year, I started diving into C++, and Blueprint and all that sort of stuff. And even just from that kind of like entry level limited stuff, I'm seeing things with StateTree that I'm just like, oh, I could have just done that instead, and that would have been way simpler. So it's very, very cool tech. I see another question here of how do you take advantage of the utility state selection while still having states that can't fully know when they can run until they have performed an async action, like an EQS query.
I'll say, Jacob, would you like to tackle that one, or I know you've done a lot of
Sorry,
work on the utility.
I didn't completely sure about the
Yeah.
question. Could you repeat it?
Yeah. How do you take advantage of utility state selection while still having states that can't fully know if they can run until they have performed an async action, like an EQS query?
So I think it's two stages. Like utility selection happens when in the state selection stage, and currently the state selection happens like synchronously. There's no time slicing. There's no async. So once the state selection is done, like the utility selection is done, then you get the new selected states, and then you start your state tasks. And the task could be sync, could be async. Yeah.
So similar utilities consideration are ran at the same time as we're running the enter condition. So if you need some information before, like a EQS query, you need to execute it for doing a transition. And what end up happening more of the time when people want to do something like that, they have a transition, they have a temporary state. So they're going to go to that temporary state where they're going to do the EQS and all those query. And once those are completed, then it will run another transition that will that function will then be able to be used in an enter condition or a utility consideration.
Great. We have another question here. I've been struggling to debug StateTree. I think we kind of talked about this a little bit. Sometimes breakpoints don't work and the state trees aren't easily diffable in version control. What's the best approach for debugging them?
I agree that sometimes, like what I would like to have sometime is like a C++ breakpoint, stop or blueprint breakpoint, stop right there so I could debug right there. That would be useful. But the debugger that we looked at is the only tool that we fully support right now to do pretty much everything. It should do. You should never, if you have the break, if you enter to a state, you should get your breakpoint. If not, it's a bug. And everything the person mentioned should work. So either it's a bug or we need to figure out what's going on. But I feel that James, you think about other ways it could not work.
So I was trying to think. I was like, it should work. I was just playing around with mine this morning, trying to get things going. And I was breaking on state enter. If we're missing one, I don't know what's causing it. It might be. I don't believe we break on state enter unless you have the rewind debugger open. Like I think you have to actually have the debugger running for these breakpoints to hit. So if you've just set the breakpoint, but you don't have the rewind debugger going, I believe it just skips over it because it doesn't see it as a valid breakpoint. So it might be that you need to have the rewind debugger open, and I don't think we said that like explicitly somewhere on the UI that it needs to be open for breakpoints to work.
Or you cannot put a breakpoint if the debugger is not open, but not if it's not recording. There's no mention. So yeah. And also, you have to make sure your actor is correctly selected if you want the breakpoint to work. So, like Blueprint, you can say all the actors or that specific actor. So that could be a reason why.
Great. A couple more questions here. These are like kind of common state tree questions. My enter condition always fails for my state, but I know the data should pass.
All right, I'll take that one. That's usually happening because you're trying to bind one of your input condition or your inner conditions inputs into a task that needs to run to give you something. Usually it happens because like you're binding to a task a little bit higher in the hierarchy, but you're trying to cascade down. You haven't actually entered that state yet, so we haven't run the task. So when you get that, you're getting whatever the default value is for that variable. So if it's a location, for example, a vector, you're going to get a 0 vector and then wonder why in the world did I go to a 0 vector? Because like I know this thing should have run and given me a location for an actor, but why is this not going down? That's almost always the case of the inner conditions not working correctly, is because it's relying on another piece of data that hasn't run. So just because you're bound to a task output does not necessarily mean that we run the task before we run the inner condition. I know it seems awkward, especially when you're first working with it, because you're like, but I bound to the output, so like, why don't we run that? But the task hasn't run because we haven't entered the state yet. So usually on that, that's like Patrick said, like enter the intermediate state, and then after that's done, if it's valid, then we can try transitioning into the child states to make sure if these work or not.
Yeah. I wanted to add a little bit more to that, especially if it's when you're authoring a custom task, um, especially in Blueprint. Be careful about how you categorize your variables, right? I noticed one of the reasons why I did the double binding trick on input and output on the same parameter was because output variables are usually just going to have the default value, and whenever you enter, they're going to reset to the same value. There are a few other cases that I've come up with where this actually happens, especially when I run into another one where you bound parameter from a parent state tree and try to pass it to a linked asset state tree. Some of the bindings didn't work, so those would be some of the points where you need to be careful with. And there's usually workarounds for this. The execution data is one of those. Jake, I think you mentioned state tree property references as another one, right?
Yeah.
Cool. So yeah, be careful about how you categorize your variables, and that would be one of the things to look at if some of your tasks are not working correctly.
And back to the field end condition, there's another flag. Do you want to check the end condition only for this state, or do you also want to check all the end condition for your parent states when you're transitioning to the target state? That could affect whether it pass or not.
Perfect. Perfect. Well, I know we are running up on time here. I want to be mindful of your folks' time and not take you all day, although I'm sure we could absolutely do that. In the tradition with Inside Unreal, I have to ask one final question, which is, of all the advice, all the takeaways, all the use cases, any of these sorts of things that you could bestow upon the community watching right now, what is that one bit of advice, that one trick, that one tip, that one thought, any of that you would give to the viewers watching right now? I know it's a pretty heavy question.
Like, be friendly to everyone else around you. I know it's probably not what you wanted, but that's the first time it came in my mind.
Awesome.
So one thing that I would say is get some practice with the system, right? Especially if you come from Blueprint or C++ coding before that. The way that your mental model for building a state tree is going to be a little different than the way that you would structure something on a traditional programming language, because of the everything that Patrick and James covered, right? There's a very specific order to how things evaluate, how tasks run, and how you get data valid for binding and all of this. It's not anything that you're not going to be able to figure out very quickly, but it can be different from what you're used to on the first times that you run it, right? So the best way to just go over that is to just get some time with the tool, get your first 60 minutes with StateTree done, and then you are going to be able to use the tool for more and more and more things as you go.
Perfect.
I'll say, I guess my number one advice for people is to start in a test map. Don't throw it in like your huge giant level that you've got with a billion things running. It's very hard to then define like what the small little wrinkles are. Put it in a test map, run the debugger. It shows all the values that we're looking at every time that it takes, or every time like that it does logic. It is hugely invaluable. And if you're trying to watch something like while it's live in the level and you want to know what's going on with one particular AI, gameplay debugger. It still runs under the behavior tree category on the gameplay debugger, but it will show you state tree values as they're being updated, as well as like what active states are running. So you can kind of follow it while it's live. So you're like, what state is this thing really in? Like, why is it not doing what I expect? And then you can use that to kind of go into and be like, oh, it's because I don't have any transition or an event that would actually handle going from this particular state that it's in over to the one that I want. Which, yeah, debug as much as possible. And
yeah, absolutely.
I would
Jacob, do you have
say
anything?
Not much. I would say if you're unsure about anything, something in, let's say in a tag, always, and put a breakpoint there, start debugging and read all those variables, values, and read the code, play with it, see the expected outcome. Is that what you expect? Yeah, that would be the best way to figure out how things works under the hood. Yeah.
Perfect. Well, thank you folks so much for coming on and talking StateTree with us. This was a really great presentation. Honestly, I really loved it. And for anybody watching who may have joined in the middle or had to dip out early, we post all of these sessions in VOD format on our YouTube channel. They will also exist on the Twitch channel and as a VOD. So check back, reference it. If you're like me, it's going to probably take you a time or two of watching it to really digest everything, just because there's so much great information here. But we have that there. But with that, that is going to wrap up today's Inside Unreal. A huge thank you to the wonderful guests for today, and a huge thank you to you all for watching as well. This show wouldn't be what it is without you, your questions, and your time. And if you came partway through, yep, I already said that part. So. You can also keep up with the latest news, shoutouts, and other cool information on our socials at Unreal Engine. And if you haven't already, come join us on the Epic developer community, where we have our documentation, tutorials, both from the community and Epic staff alike, forums, and so much more. But with that, thank you all so much, and we will see you next week with something pretty cool. You might want to come back and check it out. So thanks again, everybody.
all right.